What lies beyond the observable universe? As we gaze into the celestial tapestry, our understanding stretches from the familiar glow of our solar system to the enigmatic dark spaces that challenge every truth we hold dear. From the rudimentary lenses of Galileo, which first charted the moons of Jupiter, to the intricate orbits of modern space telescopes capturing distant galaxies, our tools for probing the cosmos have evolved dramatically. Yet each discovery peels back only a layer of more profound mysteries ahead. The intriguing presence of dark matter and dark energy suggests that much of the universe is shaped by substances and invisible forces, dictating the speed at which galaxies rotate and the universe expands. But could there be more than our universe? The theory of the multiverse proposes a spectrum of possibilities where different laws of physics may apply. Each discovery, from black holes bending the fabric of space-time to gravitational waves echoing through the cosmos, is a puzzle in understanding the broader cosmic picture. These cosmic phenomena challenge our perceptions and invite us to contemplate the more profound mysteries that define our universe and possibly others. Are we ready to redefine our understanding of the cosmos and accept the boundless realms of the multiverse? This narrative challenges our perceptions and invites us to explore the profound implications of what lies beyond the observable universe. As humankind has plumbed the depths of the universe, it's begun to encounter phenomena that our traditional understanding of physics could not describe. Among them are dark matter and dark energy, components of the cosmos that remain invisible to our telescopes, but profoundly affect the structure and fate of the universe. The mystery of dark matter first arose from the study of the rotation curves of galaxies. According to Newtonian mechanics, stars at the galaxy's outer edges should rotate slower than in the center, like the planets in our solar system. However, observations have shown that this is not the case. Instead, the rotation rate of stars and galaxies remains constant, suggesting that there is an invisible mass exerting an additional gravitational force. This matter, detectable only through its gravitational influence, forms the entire skeleton of the universe. Turning our gaze from the hidden mass inside galaxies, we encountered an even more elusive component: dark energy. This mysterious force drives the universe's accelerating expansion, a phenomenon first detected by the strange behavior of distant supernovae. Instead of slowing down, as one might expect from the gravitational pull of the entire universe's mass, its expansion is accelerating. Among these expansive forces, black holes anchor the cosmic drama. Born from the collapsing cores of massive stars, these gravitational giants warp space-time to the point where even light cannot escape their grip. The first direct image of a black hole's event horizon revealed a universe stranger and more fantastic than we could have imagined. And rather than providing new answers, it only added questions to those already existing. However, the interaction of these cosmic giants is not silent. When black holes merge, they send gravitational waves throughout the universe, rips in space-time that we've only recently begun to detect. Observatories like LIGO and Virgo are capturing these waves, giving us new insights into some of the most violent events in the universe. Gravitational waves have opened a new channel through which we can explore the cosmos, complementing the electromagnetic spectrum that's been our primary window into the universe. By analyzing these waves, scientists can unlock the secrets of black hole masses, rotations, and merger details, enriching our understanding of the fundamental physics that governs the most extreme objects in the universe. But this is only part of humanity's quest to understand the cosmos's cruel mechanisms and find potential cradles for life throughout the universe. The search for exoplanets and the search for extraterrestrial intelligence represent two journeys into the unknown. guided by our deep curiosity about the cosmos. The discovery of myriad worlds orbiting stars within our galaxy has opened a new chapter in our understanding of the universe, expanding our horizons beyond our solar system to include many planets with conditions as diverse as those on Earth. Each discovery, from the sultry surfaces of hot Jupiters to the potentially habitable conditions on super-Earths, becomes the basis for a broader story about our place in the universe. With its unprecedented observational capabilities, the James Webb Space Telescope allows us to peer into the atmospheres of these distant worlds, analyze their composition, and look for signs of life. This bridge to the stars is not just about discovering new planets. It's about understanding the conditions that can support life, a question that naturally extends to the search for signals from civilizations beyond our planet. Meanwhile, an initiative known as the Search for Extraterrestrial Intelligence, or SETI, has continued for decades to explore the silent expanse of space, listening for faint whispers of civilizations that may exist in these distant worlds. Use of technologies covering a vast electromagnetic spectrum, SETI's efforts underscore the enormity of our search and the tantalizing possibility that we are not alone. At the heart of SETI's theoretical foundation is the Drake equation. Formulated by astronomer Frank Drake in 1961, the equation offers a way to estimate the number of active, friendly, extraterrestrial civilizations in the Milky Way galaxy. The equation considers factors such as the star formation rate, the fraction of stars with planetary systems, the number of planets on which ecosystems can develop, and the likelihood of intelligent life. The equation highlights the vast number of unknowns in this search, from the fraction of habitable planets with life to technological civilizations' longevity. Nevertheless, searching for the potential for life in space is only the beginning. The deeper we delve into the mysteries of the cosmos, the more our knowledge expands, and the more questions arise. The constant change in our understanding of the cosmos lays the groundwork for considering even more possibilities. The enigmatic phenomena discovered in the course of these investigations, the invisible scaffolding of dark matter, and the pressure of dark energy on the expansion of the universe, provide the basis for considering the multiverse not as science fiction, but as a plausible structure that can explain mysteries that remain beyond our current scientific reach. Our current search, limited to the observable universe and based on our understanding of life on Earth, can only scratch the surface of what's truly possible. Multiverse theory opens up an even more comprehensive range of possibilities, reaching beyond our observable universe into realms where the fundamental laws of physics may be radically different. The Drake equation, which is the basis for our search for extraterrestrial intelligence by estimating the number of friendly civilizations in our galaxy, operates within the physical laws of our universe. However, if we embrace the multiverse theory, the equation may be just one of countless ways to understand the potential for life in a more extensive and diverse multiverse landscape. In general, the multiverse concept pushes the boundaries of our cosmic understanding into new, uncharted territories. It suggests that our universe, as vast and complex as it is, may be only one of a vast number, perhaps an infinite number, of universes existing parallel to our own. The seeds of the multiverse theory are in quantum mechanics and cosmology. With its probabilistic nature, quantum mechanics introduces the idea of parallel outcomes arising from the same quantum events. If we apply this principle to cosmological scales, we can assume that in the universe, each possibility is realized in its own separate cosmos. Cosmic inflation, a theory describing the exponential expansion of the early universe, provides another basis for a multiverse. Inflation suggests that bubbles of space may have formed, each expanding into its universe with a larger multiverse. These bubbles may have different properties and physical laws dictated by the nature of the inflationary field in each region. Most conceptions of the multiverse are not monolithic. They include several models, each with its implications for our understanding of reality. Bubble universes emerging from the theory of cosmic inflation. Bubble universes are distinct regions within a large space, each having undergone its inflationary expansion. These universes can radically differ from our own, with different physical constants and laws. Quantum multiverses, based on quantum mechanics. This interpretation asserts that each quantum decision point generates a new parallel universe. Every conceivable outcome of any event generates its universe, resulting in an almost unimaginable variety of parallel histories and futures. Mathematical universes. This model assumes the existence of all mathematically possible universes. If physical laws, as we understand them, are merely mathematical structures, then all structures that can be described mathematically exist as tangibly as our universe. For example, let's look at the type of multiverse classified by astrophysicist and cosmologist Max Tegmark. Level 1. The Infinite Universe. At the first level of the Tegmark model, the universe extends infinitely beyond the observed cosmos. At this level, it's assumed that our observable universe, 92 billion light-years in diameter, is just an infinitesimal particle in an increasingly vast cosmic landscape. Every structure, event, and variation is infinitely repeatable in space, suggesting that our duplicates exist somewhere in similar conditions, if not identical. Level 2. The Post-Inflationary Multiverse. The second level of Max Tegmark's multiverse model explores the realm where individual universes arise from their own unique Big Bang events. This classification is rooted in the concept of chaotic inflation, which assumes the existence of a cosmos in which our universe is just one of countless others, generated by inflationary bubbles. Chaotic inflation assumes that the rapid expansion of the universe, which we think of as the Big Bang, is not a single event, but a common phenomenon throughout cosmic history. In this model, inflation never stops completely. It stops only locally, like bubbles forming and separating in boiling water. Each bubble becomes a new universe with potentially different physical constants. In these individual universes, the fundamental constants and even the laws of physics can change from bubble to bubble. These differences can lead to universes that are radically different from our own. For example, gravity may be stronger in one universe, affecting the formation and evolution of stars and galaxies. In another, different levels of electromagnetic forces may change the chemistry of life, of course, if life is even possible in it. To understand the implications of changing these constants, imagine throwing a ball in a universe where gravity is 3 times stronger than it is here. The ball would not fly as far or as high, fundamentally changing games like basketball or soccer. If you extend this analogy to celestial mechanics, you can imagine that planets could orbit much closer to their stars, and stars could be smaller and burn up faster. If physical constants can vary so widely, then the conditions that led to the emergence of life on Earth are just one possibility of a vast cosmic lottery. Each universe may be a unique experiment to explore the possibilities of physical reality. Although second-level multiverses differ fundamentally in their constants, they share a common link with their first-level multiverses, where all the laws of physics are constant, but the initial constants vary. This multi-level structure of the multiverse not only expands our understanding of what's possible, but also provides a basis for understanding the incredible variety of conditions under which universes can form. Level 3. The Many Worlds Interpretation of Quantum Mechanics. Perhaps the most disconcerting of Tegmark's levels, the third level, introduces the concept of quantum mechanics into the multiverse theory. According to the interpretation of multiple worlds, every possible outcome of every event defines or gives rise to a new world or universe. This level assumes infinite timelines and possibilities where each conceivable scenario takes place in its own universe. Imagine a simple everyday decision, such as turning left or right on your way to work. In the many worlds interpretation, each choice results in a branching universe. One version of you turns left, while another version turns right in a parallel universe. These universes exist simultaneously, but do not interact with each other, and each follows its path of reality based on that single quantum decision. Another example is the flip of a coin. In our everyday experience, the coin falls either heads or tails. However, in the context of the many worlds interpretation, at the moment of the coin flip, the universe is split into two, one where the coin falls heads and one where it falls tails. Each outcome exists in its separate universe, and the consequences of this simple event spread outward, affecting further events in each respective universe. However, this interpretation goes beyond human-scale events and encompasses all quantum events in the universe. For example, the same decay of a radioactive atom, a fundamentally random process at the quantum level, would cause the universe to split into one in which the atom decayed and one in which it did not. Each of these universes would continue to evolve independently, accumulating its unique history. The fascinating aspect of this level of the multiverse lies not only in its scientific implications, but also in the way it reflects the complexity of human choices and the inherent unpredictability of life. Just as we can ponder what-if scenarios regarding our past decisions, the interpretation of many worlds realizes these alternatives in countless parallel universes. Level 4, Ultimate Ensemble. The fourth level of Max Tegmark's multiverse classification represents the most radical and profound conception of all possible universes. In this model, known as the mathematical universe hypothesis, reality is viewed as a landscape of mathematical structures. Each structure defines a separate universe, distinguished not only by physical constants or laws, but also by potentially entire mathematical structures. According to the hypothesis of mathematical universes, our physical world is not just described by mathematics, it is mathematics. This means every conceivable mathematical structure exists as a physical reality somewhere in a multiverse. These universes may function based on entirely different mathematical rules than the ones we know and understand. To illustrate this profound concept, let's take a simple object like an orange. Imagine holding an orange in your hand. It's familiar and tangible, but this orange is a set of mathematical properties at its core. The shape of the orange, the ideal sphere, is not just a physical form, but a geometric expression that describes contours and volume, defining how the orange exists in space. Now, think about the orange color that we see. This bright hue is not just a random feature. It results from light interacting with molecules on the orange's surface that absorb and reflect light at specific wavelengths. Because the science of light, optics, is deeply mathematical, it relies on equations that describe how light behaves when it encounters an object. Even the taste of an orange, the combination of sweetness and acidity, is driven by chemical reactions that can be quantified and predicted with mathematical precision. The concentrations of sugars and acids are subject to chemical laws, essentially mathematical relationships that determine how substances interact. Every aspect of an orange, from its growth to the sensations it evokes when we eat it, can be described using math. In this way, this simple fruit becomes a small, tangible proof of a much larger truth. Our entire universe, from the smallest atom to the largest galaxy, can be part of a grand mathematical structure. If we accept that every mathematical structure corresponds to a physical universe, the implications for science and philosophy are enormous. It implies that any universe that a consistent set of mathematical rules can describe exists as surely as our own. It implies that universes with radically different properties that defy our physical intuition are just as real as our own. Consider a universe in which the dimensions of space and time are not 4, as in our visible universe, but 5, 10, or even more. The behavior of particles and forces in such a universe could be radically different, changing the process of matter formation and evolution. Or imagine a universe governed by a different type of geometry, where the shortest path between 2 points is not a straight line, but some other curve, which radically changes the structure of the universe and the life it can support. Level 4 is connected to the other levels of the multiverse, providing the ultimate framework, while levels 1 to 3 deal with the universes that differ in initial conditions, physical constants, or quantum results. Level 4 encompasses all possible mathematical realities. It offers a cosmos where the boundaries of possibility are limited only by the limits of the mathematical imagination. The implications of the multiverse theory go beyond physics and into philosophy, forcing us to think about the most fundamental concepts of reality, causality, and existence. If the multiverse is real, it means that with all its complexity and beauty, our universe is just one of countless others, each with its own history, laws, and perhaps even life forms. In the scientific realm, the multiverse theory raises profound questions about the nature of scientific inquiry and evidence. Since other universes in the multiverse are, by definition, beyond our observation, the theory walks a fine line between physics and metaphysics, forcing us to reflect on views of the principles of empirical science.
That's one small step for man, one giant leap for man.
As we ponder the vastness of the universe and the possibility of countless worlds in the multiverse, our quest for space exploration continues to propel us forward. The next chapter in human space exploration is being written now, with ambitious programs and missions that aim to expand our presence beyond Earth, back to the Moon, onward toward Mars, and eventually beyond our solar system. In conjunction with international and commercial partners, NASA's Artemis program marks a major milestone in our efforts to explore the Moon. Named after Apollo's twin sister, the Artemis program aims to return humans to the Moon by the mid-2020s, with the lofty goal of a sustained human presence there by decade's end. Unlike the Apollo missions, which were short-term visits, Artemis envisions a long-term presence of humans and robots on the Moon, utilizing its resources and using it as a testing ground for technologies needed for deeper space exploration. The Artemis architecture includes Gateway, an orbital lunar outpost that will support long-term human missions to the Moon and serve as a transfer point for missions to Mars and beyond. Gateway will facilitate scientific research, provide a platform for testing new technologies, and usher in a new era of the international cooperation in space. In turn, the red planet Mars has long captured our imagination as the next frontier for human exploration. Based on decades of robotic exploration, plans for manned missions to Mars are taking shape to send astronauts to Mars in the 2030s. These missions will require improvements in life support, propulsion, and habitat technologies, and a better understanding of the psychological and physiological effects of long-duration space travel. Human missions to Mars will aim not only to answer fundamental questions about the planet's history and geology, but also to search for signs of past life, test the possibility of existence on Martian soil, and lay the groundwork for future colonization. While the Moon and Mars are within our reach, the ultimate challenge is interstellar travel, expeditions to other star systems. One of the most visionary projects in this area is Breakthrough Starshot, an initiative to build a fleet of light-sail spaceships capable of traveling to our nearest stellar neighbors, such as the Alpha Centauri system. These spacecraft could theoretically be accelerated to a significant fraction of the speed of light, allowing them to reach Alpha Centauri in just over 2 decades after launch. Such missions could provide invaluable data on other star systems and potentially habitable exoplanets, paving the way for future interstellar exploration. The journey to the Moon, Mars, and ultimately to the stars is not just a series of missions, but but a continuation of our fundamental quest to explore, to understand, and connect with the universe around us. Even stepping into the next chapter of human space exploration can push the boundaries of our technological and scientific capabilities and inspire future generations to dream of the possibilities that lie beyond our cosmic horizon. Imagine a single point, just a speck of light, hovering in an endless sea of darkness. It's not just a random dot, it's our home, Earth. But what if we told you that this dot is just a fleeting moment in a cosmic panorama so vast and complex that it defies human comprehension? Imagine a night sky decorated with stars, each representing a sun, many of which have their own planets. Now, multiply that image by 100 billion. Even in this case, you've barely touched the surface. Beyond our Earth, beyond our Sun, even beyond our galaxy, lies a structure so vast that everything you know seems like a single thread in an unfathomable cosmic web. The human mind, which is itself a marvel, struggles to grasp this scale. Our brains are built to comprehend the rises and slopes of mountains and the vastness of oceans. But how do we comprehend a structure that stretches billions of light years? Today, we're on a journey to explore these galactic threads, the sinews and muscles of the universe itself. We will venture into a realm of the almost incomprehensible, where even the speed of light seems pedestrian. Spiders weave intricate webs, thin but strong, each thread connected to the other in a complex pattern. Architects of nature create these webs to survive, capture prey, and probe the environment. Now, imagine a web woven not by spiders, but by the very fabric of space and time itself. A web that links galaxies, star clusters, and dark matter into a complex web. This is the cosmic web, the grand architecture of our universe. Each node you see here is not a single star or planet, but an entire galaxy, a colossal cluster of billions of stars, planets, and other celestial objects bound by gravity. But what gives this network this structure? The answer lies in something we can't even see: dark matter. Dark matter, which scientists believe makes up about 27% of the universe, acts as the framework on which this web is built. Although invisible, its presence is felt through the gravitational pull that determines the formation of galaxies and the paths they take. The cosmic web was not always as we see it today. It evolved over billions of years, beginning with tiny fluctuations in the density of the early universe. These fluctuations grew, pulled together by gravity, eventually forming the majestic filaments and nodes we now see. One of the most impressive examples of a galactic filament is the Great Wall of Hercules' northern corona. This colossal structure spans a distance of up to 23 billion light-years, making it one of the largest known structures in the universe. Understanding this network is not just an academic exercise. It's a quest to understand our place in the universe. Are we simply an accidental byproduct of cosmic evolution? Or is there a grander design at work here? Scientists use a range of tools to study this network, from telescopes that can see distant galaxies to simulations that model the behavior of dark matter. Each discovery is a piece of the puzzle, a thread of a story that spans the entire universe. Here it is, Earth, a pearl of blue and green, suspended in the vastness of space. A planet teeming with life, from microscopic to magnificent. It's easy to think of the Earth as the center of everything, but in the grand scheme of the universe, it's just a speck. In our solar system alone, Earth is only one of 8 planets orbiting the Sun, and yet it stands out for its unique ability to support life. The oceans, the atmosphere, the magnetic field, all these elements are in delicate balance. Zoom out even further, and our entire solar system becomes a tiny dot in one of the spiral arms of the Milky Way galaxy, a galaxy that's home to hundreds of billions of stars, each potentially containing its own system of planets. In the Milky Way, it's just one galaxy in a cosmic web of hundreds of billions of galaxies. Each of these galaxies is a node, a focal point in this unimaginable structure. Even within our galaxy, the Earth is influenced by forces beyond its control. Dark matter, the invisible backbone of the cosmic web, shapes the structure of the galaxy and, as a result, the environment around the Earth. Yet despite its seemingly insignificant place in the cosmos, Earth is unusual for one reason. It has life. It's the only known celestial body where life not only originated, but has evolved to an incredible level of diversity and complexity. Humanity's quest to understand its place in the universe has led to remarkable scientific advances. Telescopes peer into remote corners of the universe, and supercomputers simulate the cosmic web, helping to answer fundamental questions about the nature of reality. For example, look at the sun, the blazing ball of plasma that lights up our sky and warms our planet. It's the reason you can see these very images, the reason life exists on Earth. But in the context of the cosmic web, the sun is just one node, a lone star among countless others. Close to the sun, we find other stars, some smaller and cooler, others larger and hotter. Each of these stars is like a bead on a huge cosmic thread, linked together by gravity and dark matter. Our sun is located in the Orion sleeve of the Milky Way, a small spiral arm located about 27,000 light-years from the center of the galaxy. Even within our galaxy, it is far from special, just one of about 400 billion stars. In the great expanse of the cosmic web, stars like our sun form complex nodes that connect larger structures, such as galaxies and galaxy clusters. They are the building blocks, the fundamental units that give the web its shape. So what powers this celestial beacon? The answer is nuclear fusion. Deep in the sun's core, hydrogen atoms collide and fuse to form helium, releasing massive amounts of energy. This energy not only powers the sun, but also balances the gravitational forces trying to compress it. This energy has far-reaching consequences. It provides the Earth with the heat and light necessary for life. It drives our weather systems, powers photosynthesis, and even influences Earth's climate over the long term. Understanding the sun is crucial to understanding the cosmic web. Various missions, such as the Parker Solar Probe and the Solar Dynamics Observatory, have been launched to study the sun's behavior. These missions provide insights into solar cycles, magnetic fields, and even the future of the sun. Although the sun serves as a vital node in the cosmic web, nourishing life on Earth and influencing our local space environment, it's just one example in a universe teeming with stellar diversity. Every star, regardless of its size or lifespan, plays a role in shaping the cosmic web. From the tiniest red dwarfs to the massive blue giants, each star is a unique knot contributing to the overall structure of galactic filaments. Stars are often classified by their mass and brightness and plotted on a graph known as the Hertzsprung-Russell diagram. This diagram shows the life stage of a star and gives clues about its future fate. Take, for example, a red dwarf, the most common type of star in the universe. They're small, cold stars, also called M-type stars. Often less than half the mass of our sun, they make up for their lack of size with longevity, burning for tens to hundreds of billions of years. Red dwarfs are frugal. They turn hydrogen into helium much more slowly than larger stars. This slow lifestyle allows them to be among the longest-lived objects in space. Now compare that to O-type stars, the rare titans of the stellar world. These stars are more than 15 times more massive than the Sun and can be 1,000,000 times brighter. Yet they live fast, die young, often in spectacular supernova explosions. O-type stars dramatically end their lives. They collapse under their own gravity and then explode as supernovae. These explosions scatter elements such as carbon, oxygen, and iron into space, promoting the formation of new stars and planets. Star clusters are like cosmic nurseries, places where stars of different types are born. These clusters serve as nodes in the cosmic web, linking different regions of a galaxy and even connecting galaxies to each other through filaments. Computer simulations help astronomers understand how different types of stars contribute to the cosmic network. These virtual models can simulate billions of years of cosmic evolution in a matter of weeks, showing how stars serve as the building blocks of larger cosmic structures. So, we've already found out, stars are not eternal. They are born, live, and eventually die. The life cycle of a star is a cosmic journey spanning billions of years, a journey that plays a key role in the evolution of the universe and the structure of the cosmic web. The birth of a star is a spectacle of cosmic proportions. It begins in a nebula, a vast cloud of gas and dust. Gravity pulls these particles together, getting denser and hotter until nuclear fusion ignites. A new star is born. Once a star reaches the main sequence stage, it enters a period of relative stability. The hydrogen in the core turns to helium, releasing energy that balances the gravitational forces trying to compress the star. This is the longest phase of a star's life, and it's where our sun is now. But even stars like our sun must face change. In about 5 billion years, the sun will run out of hydrogen fuel. Its core will shrink, but its outer layers will expand, turning it into a red giant. This phase is the prelude to the final fate of the star. Depending on its mass, the star will meet one of several ends. Stars with less mass, such as our sun, will shed their outer layers, leaving behind a white dwarf. More massive stars may undergo a supernova explosion, resulting in a neutron star or black hole. These deaths are not in vain. The death agonies of stars scatter important elements into space, elements that will become the building blocks of new stars, planets, and even life. Thus, the life and death of stars is an integral part of the cycle of cosmic creation and destruction. The cosmic web, from individual stars to entire galaxies, is a complex network of interconnected structures. But what binds these galaxies together? What are the threads that weave the complex fabric of the universe? The answer lies in galaxy clusters. Galactic clusters are massive collections of galaxies bound together by gravitational force. They may contain only a few or thousands of galaxies and often span millions of light years across. Just as dark matter plays a role in individual galaxies, it also acts as an invisible glue in galactic clusters. Even though we can't see it, we know it exists, holding the cluster together and forming its overall structure. Within a cluster, galaxies are not static. They are in constant motion. Some of them may be heading toward the center of the cluster, while others may be on their way to its edge, under the influence of complex gravitational interactions. Sometimes these interactions can lead to dramatic events, such as galactic collisions. When galaxies collide, their stars, gas, and dark matter merge to form a new, larger galaxy. These events are crucial to the evolution of galaxy clusters, and, by extension, the cosmic web. But clusters are not the end of the story. They often cluster together to form superclusters, which are among the largest known structures in the universe. These superclusters serve as the main nodes of the cosmic web, linking numerous clusters and filaments. Understanding galaxy clusters is the key to unlocking the mysteries of the cosmic web. They serve as threads connecting galaxies,
forming the paths along which matter and energy flow on cosmic scales. Having studied the colossal structures of galactic clusters, the threads that weave the cosmic web, we now turn our eyes to an even more mysterious phenomenon. What if there were actual threads, strings of pure energy that stitch together the fabric of the universe? These hypothetical one-dimensional defects in space-time could be the loose threads of the universe, remnants of the first moments after the Big Bang. Imagine the universe just moments after the Big Bang, a hot, dense state of pure energy. As the universe cooled and expanded, this energy condensed into matter and structure. However, not everything went smoothly. In some regions, kinks occurred, leading to the formation of cosmic strings. Cosmic strings, if they existed, would be unimaginably thin but incredibly dense. A string less than an inch wide could weigh as much as the Earth. They would stretch across the vast expanse of the universe, perhaps even from one end to the other. Because of their enormous mass, cosmic strings would exert a strong gravitational pull, affecting the motion of galaxies and even bending light. They could serve as cosmic highways, directing the flow of matter and energy through the universe. The search for cosmic strings continues. Scientists are using a combination of theoretical physics and observational astronomy to search for these elusive structures. If the existence of strings is confirmed, they may become the missing links that will help us understand not only how the universe is organized, but also why it is organized this way. However, let's return to structures of unfathomable scale. Superclusters. They are the gravitational anchors that hold together vast networks of galaxies and galaxy clusters. Imagine moving away from our Milky Way galaxy, past our local group of galaxies, and even beyond our local Virgo supergroup. You'll find a network of superclusters, each containing hundreds to thousands of individual galaxies bound together in a complex dance of gravity. The superclusters are unevenly distributed. They form a kind of cosmic skeleton around which galaxies and galaxy clusters are located. This skeleton gives the cosmic web the shape that defines the large-scale structure of the universe. Within the supercluster, galaxies and clusters are in constant motion under the influence of the collective gravitational pull of the entire structure. This dynamic flow of matter and energy is what keeps the cosmic network alive and ever-changing. Among the most intriguing aspects of superclusters is the presence of gravitational anomalies like the Great Attractor. These are regions with such a strong gravitational pull that they influence the motion of the entire supercluster, serving as the pivots of the cosmic web. Understanding superclusters is crucial to cosmology. They serve as the largest laboratories for studying the expansion of the universe, the distribution of dark matter, and even the mysterious force of dark energy. The observable universe is estimated by scientists to contain 2 trillion galaxies. And yet, what we can see represents less than 5% of the universe. Standing over the precipice of cosmic understanding, we are humbled by the scale and complexity of the universe. From the smallest particles to the largest galactic filaments, each element serves as a piece of the puzzle. Here we are, a pale blue dot, a mere speck in the cosmic web. Yet, it is from this vantage point that we've begun to unravel the deepest mysteries of the universe. Armed with telescopes capable of looking billions of light years away, we become not just spectators, but active participants in this cosmic journey. And each new discovery is a step towards the answer to the eternal question that prompts all of us to ponder: what other mysteries does the universe hold that we have yet to unravel? Imagine a line, a simple,
unbroken line stretching into infinity. This line, in its purest form, represents the first dimension, a realm of length but without depth, a universe infinitely long but impossibly thin. Now, let's broaden our perspective, introduce a second line intersecting the first, and suddenly we're in the realm of the second dimension, a plane where length and width interact in harmony, but depth remains a variable alien to them. As we go one step higher, we find ourselves in the familiar embrace of the third dimension. This is where depth comes in, adding volume and substance to our world. Buildings rise, valleys deepen, and the universe takes on texture and shape. But what if we could add another layer? Time is the elusive fourth dimension that permeates our three-dimensional space. Invisible but omnipresent, it dictates the rhythm of our lives, a continuous thread connecting each previous moment with the current one, and the current one with the next. In this realm, our understanding of reality becomes more complex and broader. Here, the very fabric of the universe reveals its complexity, hinting at dimensions beyond our sensory perception. However, nature hints at even more complex dimensions. In the field of physics, theories suggest the existence of dimensions beyond our perception, necessary for the fundamental forces that govern the universe. These higher dimensions, although beyond our sensory perception, are crucial to understanding the structure of the cosmos. Join us as we try to unravel their mysteries together today, one dimension at a time. In a historical context, the concept of measurement permeates all human thought, from the abstract reflections of ancient philosophers to the revolutionary discoveries of modern physics. Philosophers once pondered the nature of existence, laying the foundations for our understanding of space. In their discussions, they questioned the very essence of reality, imagining realms beyond the tangible. As the centuries passed, these philosophical speculations paved the way for more structured inquiry into the nature of the universe. Meet the visionary Hermann Minkowski, who irrevocably changed our understanding by proposing that time and space are not separate entities, but intertwined dimensions that form the fabric of space-time. Albert Einstein, in turn, based on the foundation laid by Minkowski, presented the revolutionary theory of general relativity, restructuring our understanding of gravity, space, and time in a single continuum, forever changing the course of physics. Thus, from the philosophical quest of the ancient thinkers to the scientific revolutions sparked by Minkowski and Einstein, the journey through the evolution of spatial thinking reveals a relentless quest to comprehend the true nature of our universe. So, over time, we've come to realize that to truly comprehend the fabric of our reality, we must go beyond the three tangible dimensions into the realm of the fourth dimension, time. The concept of time as a dimension is both profound and persuasive, defining our existence and the universe as a whole. Unlike the three spatial dimensions, time has a direction. It moves inexorably forward, from the past through the present and into the future. This unidirectional flow of time distinguishes it from space, bringing to the universe a temporal structure that is fundamental to our understanding of reality. To illustrate the importance of time as a dimension, consider a simple everyday scenario: organizing a meeting. When we suggest that someone meet at a certain place, we unconsciously navigate the three basic spatial dimensions to determine where. It makes sense that if we arrived at different places, no meeting would take place. However, the when, the dimension without which the meeting will not take place, is no less important. That is, coming with your friend to the same place, but at different time intervals, you'll not be able to see each other. This intertwining of space and time is manifested in the concept of world line, the path that an object or person takes through space-time, thus representing its history and future. The idea of world lines provides a vivid illustration of how events are linked together in the fabric of space-time. For two people to meet, their world lines must intersect at a precise point in both space and time. This intersection is not just a spatial coordinate, but a space-time coordinate, the only point in the vast continuum of the universe where both where and when coincide. This principle applies not only to simple encounters but also to the fundamental workings of the cosmos. Celestial bodies from planets to stars trace their own world lines through space-time, their paths determined by the interplay of spatial positions and temporal moments. For example, the Earth's orbit around the Sun is not just a path through space, but a continuous journey through time, with each point in the orbit representing a unique moment. The integration of time as a dimension has a profound effect on our perception of the universe. It forces us to look beyond static images of space to the dynamic unfolding of events. Time allows us to understand the universe not as a set of individual moments, but as a continuous narrative where cause and effect bind our reality into a coherent whole. The inclusion of time as a dimension has catalyzed major advances in physics, particularly through Einstein's theories of relativity, which we've already mentioned. These theories not only deepened our understanding of the cosmos, but also paved the way for new research in quantum mechanics and cosmology. Einstein's revelation that time is relative, it slows down or shrinks depending on the velocity of an object, challenged the idea of a universal clock. This concept, rooted in the special theory of relativity, illustrates how the passage of time changes for observers in different reference frames. This phenomenon is confirmed by experiments, for example, with atomic clocks on fast-moving airplanes. In quantum mechanics, time as a dimension underlies the evolution of particle state governed by the Schrödinger equation. This basis is important for understanding phenomena such as entanglement and superposition, where the time dimension provides a probability distribution of outcomes. Going beyond the fourth dimension opens the door to a realm where our everyday experience and the laws of physics as we know them are fundamentally challenged and expanded. In search of a unified theory that harmonizes the principles of quantum mechanics and the general theory of relativity, physicists have ventured into the theoretical landscape of higher dimensions, where the fabric of the universe becomes even more intricate and mysterious. The fifth dimension and beyond are not just speculative constructs, but important components in the quest for a deeper understanding of the universe. In theories such as string theory, these higher dimensions offer solutions to some of physics' most challenging mysteries, including the unification of fundamental forces and the nature of gravity at quantum scales. The difficulty in visualizing higher dimensions is that our perception is inherently three-dimensional. Therefore, analogies become an invaluable tool. One of the classic analogies to help understand the concept of higher dimensions is to imagine the perspective of a two-dimensional being, often called a flatlander, living in a flat two-dimensional world. This being can move forward and backward, left and right, but has no concept of moving up and down because these dimensions do not exist in its two-dimensional experience. Imagine a three-dimensional sphere passing through this two-dimensional world. To a flatlander, the sphere would first appear as a dot when the sphere is just touching the two-dimensional plane, gradually increasing into a circle as more of the sphere passes through the plane, and then decreasing again to a point as the sphere leaves the plane, before disappearing altogether. A two-dimensional being would perceive this event as a circle that appears out of nowhere, changes size, and then disappears, without realizing what three-dimensional object is causing the phenomenon. String theory, the leading candidate for a unified theory, posits that particles are not the individual points we see them to be,
but tiny vibrating strings, whose modes of vibration determine the properties of the particles. This theory requires the existence of more than 4 known dimensions. In fact, it suggests that there may be as many as 10 or 11. These additional dimensions are compacted or convolved so that they are imperceptible on our scale, like the sphere in the Flatlander example. In the 5th dimension, we encounter a space containing all possible universes that start from the same initial conditions as our own universe. Imagine a tree, each branch representing a different decision or outcome leading to a different reality, all coming from the same trunk. Just as a person standing at the base of the tree can choose which branch to climb, a being with access to the 5th dimension can explore these alternate realities, each a variation of our own universe, but with slightly different outcomes. The ascent to the 6th dimension opens a plane containing all possible universes with the same initial conditions as ours, but with any possible set of laws of physics. If we think of each universe as a sheet of paper, the 6th dimension would be like a stack of such sheets, each representing a different universe. A being capable of traveling through the 6th dimension could hop between these universes, learning the different outcomes and laws governing each reality. The 7th dimension extends this concept to include universes that start from different initial conditions. To use a library analogy, each book represents a different universe. The 7th dimension encompasses the entire library, offering not just different stories, universes with the same initial conditions as ours but with different outcomes, but completely different genres, universes with different initial conditions. A 7-dimensional being could move through this library, experiencing an infinite number of universes, each with its own unique initial conditions and physical laws. In the 8th dimension, we find a web of all possible universes, each with its own initial conditions and laws of physics, as well as all possible variants of their development in time. Imagine a huge web where each thread represents the timeline of a separate universe, and each node where the threads cross represents an important event that could lead to the branching of new universes. The 8th dimension encompasses this entire web, allowing you to travel between any nodes, exploring the connections between different universes and their history. As we approach the 9th dimension, we encounter all possible laws of physics and initial conditions that have existed or will ever exist. This dimension can be compared to the art of origami, where a single piece of paper can be folded into numerous shapes. Each fold represents a change in the initial conditions or laws of the universe. And the 9th dimension includes all possible combinations of folds, resulting in all conceivable and inconceivable universes. A being living in the 9th dimension will not just have absolute freedom to cross the boundaries between all possible realms of reality, it will experience all existence and all its possible variations. The 10th dimension is the pinnacle of the hierarchy of dimensions, where all possible outcomes, realities, and existences converge. It's the space that encompasses all conceivable and inconceivable timelines for every conceivable universe, effectively encompassing all possibilities of existence and non-existence. This concept can be visualized as an infinitely complex branching tree or network, where each branch represents a different outcome or timeline, and all branches ultimately converge at one point, the 10th dimension. Visualizing the 10th dimension is challenging because of its abstract nature. One approach is to use the analogy of a tree, where each branch represents a different timeline or universe, and each leaf represents a possible outcome within that universe. Moving from trunk to leaves, we move from the initial conditions of a universe, lower dimensions, through the various choices and events, higher dimensions, that lead to all possible outcomes. The 10th dimension represents the point where all these possibilities come together, the singularity of infinite potential outcomes. It suggests a cosmos in which all possible outcomes not only can happen, but happen in some timeline or universe in the 10th dimension. The concept itself invites us to reflect on the vastness of possibilities that lie beyond our observable universe. It raises questions about fate, choice, and the underlying structure of the cosmos, prompting a broader exploration of potential realities that may exist beyond our immediate perception. The exploration of higher dimensions beyond our familiar three-dimensional space and fourth-dimensional time has profound implications for both physics and cosmology. Not only is this field of study designed to challenge our fundamental understanding of the universe, but it may also hold the key to uniting the disparate forces of nature, potentially solving some of cosmology's most enigmatic puzzles. Recognizing the existence of higher dimensions plays a key role in the search for a theory of everything, a single framework that will seamlessly unify general relativity and quantum mechanics. Currently, these two pillars of modern physics describe the cosmos on very different scales and in seemingly incompatible terms. General relativity perfectly explains the gravitational interaction of massive celestial bodies, while quantum mechanics reveals the intricate world of subatomic particles. Higher dimensions may also offer new insights into cosmological mysteries, such as dark matter, dark energy, and the nature of black holes. For example, some theories suggest that what we perceive as dark matter may be gravitational effects from matter in parallel branches, a concept from M-theory, which suggests multiple parallel membranes, or branes, as fundamental components of the universe, each potentially containing another universe in higher dimensions. Looking to the future in the field of energy, mastering the intricacies of higher dimensions could pave the way to harness forms and mechanisms of energy that we cannot now even imagine, and potentially lead to the creation of clean, virtually inexhaustible sources of energy. Similarly, the field of space travel could be revolutionized by a better understanding of the fabric of space-time, perhaps eventually enabling warp drives or other forms of faster-than-light travel. Concepts that are currently in the realm of science fiction but could be theoretically plausible within higher dimensions. The search for higher dimensions is already underway. Researchers are exploring the subatomic world with particle gas pedals such as the Large Hadron Collider at CERN, looking for evidence of additional dimensions and the particles that may inhabit them. This experimental work is complemented by theoretical studies that delve physicists and mathematicians into the abstract realms of high-dimensional spaces. As we complete our journey through the dimensions, from the simplicity of a line extending into infinity to the unfathomable complexity of the 10th dimension, we're faced with the inherent challenge of visualizing spaces beyond our three-dimensional experience. Through math, we can describe properties and relationships within higher dimensions, and physics offers theories such as string theory and M-theory that hint at the existence of these additional dimensions. Animation such as tesseracts allows us to conceptualize high-dimensional shapes and their projections or shadows in lower dimensions. Further exploration of higher dimensions promises to revolutionize our understanding of the universe. Just as the transition from a flat Earth to a spherical Earth many centuries ago broadened humanity's horizons, this expanded perception has the potential to influence not only science, but also art, philosophy, and all aspects of human creativity, inviting us to rethink the cosmos and our place in it.